We are discussing our fifth unit. In our previous lecture, we have discussed the standing waves in a string whose both the ends were fixed. Now let us discuss the second case, that is one end is free and other end is fixed. So this is our note. So standing waves in a string, one fixed end and one free end. Here let us consider a string of length L which is fixed at x equal to 0, means the x equal to 0 end is fixed and the other end, that is x equal to L end is free. So in this case the general boundary conditions are firstly y equal to 0 at the fixed end, that is at x equal to 0, y is always 0 for all values of time, and this is because this n can never move as it is fixed, so y displacement is always 0. And the second general boundary condition is del y del x equal to 0 at the free ends, that is at x equal to L, del y del x will always be 0 for all times. And this and the second one, that is this is due to the fact that the x equal to Ln is completely free from transverse force, that is there should not be any constraint, otherwise the n will not be free. So free means there should not be any transverse force. So in order to understand this case or this boundary condition, let us consider this figure of one of our previous lecture. So we know that during vibration at any point or any segment, the total y component or transverse force is t sin theta 2 minus t sin theta 1. So here it is t sin theta 1 and t sin theta 2 and then t sin theta 1. So the resultant is what? Y directional force is t sin theta 2 minus t sin theta 1. So if y directional force or transverse force need to be 0, then what happens? We must have theta 2 minus theta 2 and theta 1 must be 0. That is that is what this should be 0. And for the case of our string at x equal to L, that is for x equal to L end, we will have t sin theta 1 minus t sin theta 2 will be 0 if and only if the x equal to L end lie at the two extremum, either here or here. Then only t sin theta 1 and or t sin theta means t sin theta 2 will be 0. Here actually at this point at the extremum slope is 0. So t sin theta, y component of t is 0. So what to have the n free from any transverse force, the x equal to L n must lie at two of the extremums, either here or here. And at this point what we see, that slope is 0, slope of the curve is 0 at extremum. So del y del x equal to 0. So this general boundary condition, in this way actually we obtain the boundary condition del y del x equal to 0. So we know the general form of standing wave in a string is yxt equal to a1 e to the power I omega t minus kx plus a2 e to the power I omega t plus kx. Here a1 a2 are the two amplitude of the wave, two waves, and omega is angular frequency, k is the wave vector. So our aim is now to determine all these quantities, say a1 omega k. If we know all of them, then we will find out the final expression for the standing wave generated in the string. So in order to do so, firstly let us consider the first boundary condition, that is at x equal to 0 y equal to 0, and from and using this boundary condition in this expression for standing wave, we have similarly that a1 equal to minus a2 equal to a. So using this result here, we will get yxt equal to a e to the power I omega t minus kx minus e to the power I omega t plus kx. Now we will use the second boundary condition, that is del y del x equal to 0. So firstly we have to differentiate this expression, and then we will substitute x equal to L, means for x equal to L case, that will be the differentiation will be 0. So firstly, if we differentiate, so for example this part, so a is constant, e to the power I omega t will be common, it is t dependent part, not x dependent part, as we are differentiating with respect to x. So here we will have only minus ik e to the power ik. Here we have substituted L for x, minus ikl, and here one minus sign is already there, so ik e to the power ikl, and for s for x equal to L, del y del x equal to 0. Therefore firstly differentiating and then using this condition, we will get this to be 0. So next we have taken minus ik common, so within bracket we will have e to the power ikl plus e to the power minus ikl, and this cannot be 0. So from this part we will get 2 cos kl equal to 0. As we know, e to the power I theta plus e to the power minus I theta equal to 2 cos theta, so 2 cos kl equal to 0, and which implies cos kl equal to 0, and to have cos kl equal to 0, kl must be n plus half pi. So the possible values of k, here we have used a subscript n here because n takes values from 0 to 0, 1, 2, 3 etc., integer values. So kn equal to n plus half pi by L, and for different values of n we will have different values of wave number, and this relation will give us some other quantities, for example wavelength lambda n, which is equal to 2 pi by kn. Similarly we can obtain also the frequency, say nu n. We know lambda nu equal to velocity, so nu equal to say v by lambda n, and if we use this relation, then finally we can obtain all the quantities in terms of L. So here the general expression for the standing wave, general expression for wavelength of the standing wave is lambda n equal to 2L by n plus half. However, it is difficult to visualize the patterns of the standing wave from directly from this expression. Here we have used another expression, modified expression, where we use actually L by lambda n. So L by lambda n will be equal to n by 2 plus 1 by 4. So you will get from this expression, so L by lambda n, and then n plus half divided by 2, which will give you n by 2 plus 1 by 4. Now here actually gives us, means this expression gives us how many wavelengths or how many waves may be accommodated in the string, entire length of the string. So say for example n equal to 0, L by lambda 0, L by lambda 0 will be 1 by 4. Means what? A quarter of a wavelength fits on the string. That is, we can accommodate 1 by 4 of the total wavelength of the standing wave in the string. So quarter means, firstly we visualize here, this is a complete wavelength. If we divide this wavelength into 4 parts, so this is first quarter, second quarter, third quarter, fourth quarter. So here we will have, for n equal to 0 case, that is L by lambda not equal to 1 by 4, or lambda not equal to 4L, or L equal to lambda naught by 4. So we will have only 1/4 of the 1/4 of the total wavelength. So this is the quarter, means this portion of the wave, here to here. And here actually we need to consider the boundary conditions also. First end is fixed, x equal to 0 n, and x equal to L n is at the extremum, and that extremum point is this one, slope is 0 here. So for n equal to 0 case, a quarter of a wavelength fits on the string. Now for n equal to 1 case, in this case L by lambda 1, means if we substitute n equal to 1 in this expression, we have L by lambda 1 is equal to 3 by 4. So means what? 3 by 4, fourth of the wavelength fits on the string. That is, we can accommodate 3/4 of the total wavelength in the entire length of the string. So 3/4 means, you see, this is first quarter, second quarter, and third quarter. So we will have this portion, and this is the pattern of standing wave for n equal to 1. So this is first quarter, second quarter, and third quarter. So 3 by 4. Now for similarly for n equal to 2, we will have 5 by 4. 5 by 4 means we have one complete wavelength, means can be fitted, and along with that a quarter of the wavelength. So one full wavelength plus the a quarter. So you see here actually complete wavelength and another quarter. So in this way we can obtain the patterns of standing waves generated in a string whose one end is fixed and other end is free. So the general motion of the string with one end fixed and one end free is now yn xt equal to minus 2ia e to the power I omega nt sin kn x. So using the values of kn, we can obtain the displacement or general solution, general expression for standing wave. So here kn equal to n plus half pi by l and omega n equal to vkn. So in this way we can obtain the standard wave for the second case, that is one end of a string is fixed and other one is free. Thank you.